Okay, so in order to give a good explanation of this, I thought I'd just share this and talk instead of writing. It's much easier for you to see this. So I started with a diagram here. As we can see, we have the y direction and the x direction, our inclined plane. We've got the normal force acting perpendicular to the y, parallel to the y direction, or perpendicular to the plane. The weight of the object acts down the plane. Our distance is here given. The ramp angle is there. The only two forces are the force of gravity and the normal force, because we're not told anything about friction here. So the assumption is that the surface must be frictionless, or else you'd have to be given more information about the coefficient of friction. So I've also shown the weight broken into the y and the x components in dotted red lines there. And then I've listed the givens on the right side of the screen so you can see them. These were all given in the actual problem, except AY. We can recognize that AY must be 0 because this object is not floating off the ramp. It's not moving off the ramp at all. It's only accelerating down the ramp, which will be AX. All right, with that said, let's go ahead and take a look at what's going on in the problem. So we look at the sum of the forces always in the x and the y direction to start. And the nice part is that when we look at the x direction, what we'll figure out here is that there's only one force acting. It's the x component of gravity, that actual, that force. So really, we don't have to worry about friction. Normally there's minus FF, but this is kind of an easy problem. There's no friction involved. So we can rewrite FGX as its value, which is FG, and we want the, again, x component, so it's times the sine of the theta of the ramp there. So the ramp angle itself is 60 degrees. That's given in the problem. And remember that when you're looking for the x component, you're always going to use sine on an inclined plane of the angle itself. That's different than when you break up your components of a vector normally, where usually you're used to using cosine for the x direction. So it turns out that we have FG sine theta ramp equals MA. Well, FG is just MG. So the M's are going to cancel. Right, m's on both sides. So it turns out g sine theta is my acceleration, which is my common answer for an inclined plane acceleration, g sine theta. So if I go ahead and plug in values, 9.8 times the sine of 60, I get 8.5 meters per second squared as the acceleration. And now that is not part A, it is actually part C. So we're going to put that down for part C. I would always start the problem off with dynamics, but you could solve this problem, and I put it down here, with conservation of mechanical energy. And if you did it that way, you could get part A first without knowing the acceleration by saying that the potential energy at the top of the ramp equals the kinetic at the bottom. And then you could actually get the same answer you would get there. But we're going to do it this way because I already solved for the acceleration in the x, and you're going to need it anyway. The y direction we don't do anything with, because the y direction really only gives us Fn. And with Fn, we can use that to help with Ff. But since Ff is 0 in this problem, we don't have to worry about there being any sort of use for Fn. So no need to look at the y direction in this problem. Now, when I go to part A, it says find the velocity at the bottom of the ramp. It's released from rest, so that VO is going to be 0 there. V final squared equals V initial squared plus 2a delta x. Delta x is really the same thing as d in this case. It's the distance traveled along the x-axis. So that's going to be 30 right there. And delta x really is what? The displacement technically, right? But we're saying that it starts here and it ends there. So 30 for distance is the same as 30 for displacement. The acceleration down the ramp is 8.5. And then we put the 2 in front. 2 by 8.5 by 30. And then take the square root of that to get rid of the square. You're going to get 22.6. It's the square root of 510, I think. Part B asks us to find the weight of the object if it were on the moon. So the nice thing we can do here is go ahead and find the mass on the Earth first. So here's the weight on the Earth equals the mass times gravitational constant on the Earth. So the weight on the Earth divided by the gravitational constant gives us the mass on the Earth. And then once you know the mass on the Earth, you can multiply it by the gravitational constant on the moon, which is 1.6, as opposed to the 9.8 we used earlier, and take our mass times 1.6, and we'll get our actual weight on the moon. This number should be about 1/6 of this number that we had to start, which it is, because the gravitational pull on the moon is about 1/6 of that on the Earth. So if you want to lose weight, go to the moon. You weigh about 1/6 of your weight. So we have these two answers, FG and V. C was already answered. This is the acceleration down the ramp. We got that answer, if you recall, over here in the first part when we did our x direction work. Last but not least, we're trying to find the time it takes to slide down the ramp. Well, we have the final velocity of 22.6. Initial velocity is 0. Acceleration is 8.5. So if I drop off initial velocity, right, I get this line here, and then I divide by A, I get V over A. So 22.6 over 8.5 is going to be around 3 or 2.7 seconds to slide down the ramp. Again, note that you could do the first part with conservation of mechanical energy. I spoke quickly because I know students like quick responses, but feel free to go back, pause the video, and take a look again at the entire solution one step at a time.